Okay. Good afternoon, everyone. Welcome to College of ICT and CMLNet Research Seminar. I would like to start with acknowledgement of country. I respectfully acknowledge the traditional owner of the land on which we all work and learn, and I pay my respect to the First Nations people and their elders past, present, and future. Today we have Dr. Olatunji Omisore, who will be giving us a presentation titled Procedure Automation in Robot-Assisted Cardiovascular Interventions. I would like to give a brief introduction of Dr. Olatunji Omisore. He has obtained his PhD degree in pattern recognition and intelligent systems from the University of the Chinese Academy of Sciences. His research aims to reduce global mortality and morbidity associated with cancer and cardiovascular disease. He has worked as CASPI postdoctoral fellow and research associate professor at the Shenzhen Institute of Advanced Technology, where he has secured multiple research grants. And Dr. Olatunji's research has a profound impact with 60 plus articles published and with over 3,100 citation with H index of 28. He has 5 international patents on prototyping 3 robotic system and industrial collaboration experience. Dr. Omisore has successfully co-supervised multiple RHD students at PhD and master's level. He is also a senior member of several professional bodies, including the Institute of Electrical and Electronics Engineers, Association for Computing Machinery, and Australian Computer Society. So, Olatunji, you can start your presentation when you are ready.
Okay, thank you very much, Dr. Fariza, for the nice introduction. And I'm really glad to be given this opportunity to present my research here at the CMLNet monthly presentation. Let me share my screen first, and I would like if you can confirm being able to see my screen. Could you please confirm if you're able to see my screen, the presentation deck? All right,
Yes,
thank you very much.
we can, yeah.
Yeah, so today I will be talking about some of the research that I've carried out while at the Chinese Academy of Sciences. And this actually covers a few of my research in the last 5 years, wherein I focused on how to develop automation system for visual procedures when it comes to robot-assisted cardiovascular interventions. So typically in robot-assisted cardiovascular interventions are focused on different types of research tracks. For this particular one, I looked at how I could develop AI-driven models for assisting navigation and as well as automating the visual aspect of endovascular robot-assisted interventions. My name is Olatunji Omisore, and I have a PhD in Intelligent Systems, and I'm currently affiliated with the Center for Machine Learning, Networking, and Education Technology at the School of Engineering and Technology in Sikh University. Again, I know the acknowledgement of the country has been given, but I'd like to repeat by saying we acknowledge the traditional owners and custodians of this land where we work, study, and learn. I pay my respect to the elders of all First Nations people of Australia. So this is going to be the content for my today's presentation, and without wasting too much of time, I would want to start with the research background. Now, this actually started during my PhD days at the second year of my PhD, moving towards the third year, where my professor actually called me. Then at the initial time, I was actually working on gastrointestinal cancers. We're developing a robot for gastrointestinal cancer. And then he told me now we got a new grant and would like to focus on cardiovascular intervention. So because of that, we start developing robotic system for this kind of procedures. What is cardiovascular disease generally? Now, this is one of the major diseases that causes a lot of death globally in all parts of the world. And then it typically happens when the vessels that carries blood to the heart or away from the heart actually being malfunctioning. And because of that, it remains the leading cause of death globally. Now, cardiovascular diseases can actually be characterized in different ways. For example, we could refer to them as being cardiovascular disease when it has to do with issues that has to do with the heart or the blood vessels around the heart. It could also be cerebrovascular diseases, for example, such as stroke or anything that has to do with vessels in the cerebral region of the body. or sometimes we say this peripheral vascular diseases when it has to do with the vessels of the limbs, such as the hands or the legs, right? Now, but each one of these also has their own different characteristics. But in my research, I focus much more on the cardiovascular aspect. That is, that has to do with the heart. And again, it has a high prevalence all around the world, especially the countries with high socioeconomic index, including Australia. Of course, indices or the prevalence ratio actually looks a bit lower in Australia when you compare with so many other countries, for example, the United States or even in China. Now, but notwithstanding, the mortality rate is still very high, about 24%, which means 1 of every 4 person in Australia is going to die of cardiovascular disease. So this is actually a very big problem. Now, over time, there has been a lot of methods into how they can diagnose and carry out procedures for this kind of disease. This starts with open surgery. In open surgery, the surgeons will have to open up the cardiac area of the surgeon in order to be able to visualize and assess the vessels that are having the problem or the part of the heart that is having the problem, and come out with how they can, cure the patient. But when doing this, they actually have to open a large part of the cardiac area of the patient, which requires the patient to stay in the hospital for a very long period of time. The healing process is very slow and takes a lot of time, and they lose a lot of blood, which is not really good for the patient. Because of that, there were a lot of new approaches, and then new techniques into coming up with a new approach that can be used to solve this problem. And that is when they came up with manual endovascular intervention. Now, in manual endovascular intervention, rather than having to open up that large area in the cardiac part of the patient, they'll just need a port in the peripheral parts of the patient. For example, making a hole in the radial vessel of the patient or in the femoral vessel of the patient. And with that, they can navigate flexible endovascular tools. Now, when I say flexible endovascular tools, this actually includes catheter, guidewire, balloon, and stents that are navigated from the peripheral part into the cardiac region in order to deliver some certain drugs during the procedures. And with this means patients do not need to suffer that kind of, being exposing the whole of their cardiac area and also having to stay a long period of time in the hospital. If after the procedure, a few days after, they can go back to work, which is really good. But then surgeons are exposed to radiation. Where's radiation coming from? Now, for the surgeons to be able to visualize what is going on in the surgical scene, they use the X-ray system. And the X-ray system actually emits this radiation, which actually exposes surgeons to a lot of problems. For example, there has been research that shows that the surgeons also suffer from head and neck cancer as a result of long-time exposure to radiation. So in order to solve that problem, they propose using apron lead. Apron lead is a kind of suit the surgeon can put on to reduce the exposure to radiation. However, that is very heavy. It has a lot of weight, which results in ergonomic issues such as back pain and also not still what they want. Now, in order to bring the surgeon out of the exposure to radiation, there has been a lot of movement in the last 2.5 decades on building robotic systems that can be put into the catheterization lab, whereby the surgeon can stay away from the radiation and still control the robotic system to deliver or navigate such tools, such as what I have on the slide now. There has been a good number of robotic systems that are even commercialized, such as the Copper GRX, which has been commercialized already, used for this kind of procedures. But then there are a lot of challenges that such robotic systems are still facing. One of them is that all the control actions that with which the robotic system navigate the tools depends on the surgeon. The surgeon still be the one to make the decision, and as well as during the procedure, they need to glare their eyes on the screen in order to track the movement of the tool, which is something that is not really easy, and that slows down the procedure during the catheterization operation. Now, in my research, some of the bigger issues that I focus on for this particular track of my research is how can we actually automate the visualization parts of the procedure. That is, for instance, if you look at what I have on the slide here, we could have a start point here, and then the surgeon needs to navigate a tool from this point, from this area down into the cardiac area, right? Now, if you look at this angiogram, and by the way, this is what I refer to as angiogram. This is a typical angiogram. This from the X-ray imaging that we have in the lab then. Now, when you look at this, it's very hard for you to know or notice the 2 pixels. And again, the 2 pixels is something that is around here, like this, right? Which means for every single angiogram during the procedure, you have to glare your eyes on the screen and able to track and follow up with the movement of the tool during the procedure. So for this, I actually started research on how we can develop imaging-based method that can be used for segmenting such tool pixels in the angiograms, and then we can track its movement during the catheterization procedure. To start with, during my postdoc, I proposed an intensity-based pixel analytic method whereby we can segment the two pixels away from the angiogram. And to do that, I actually proposed this automating tool visualization and tracking method. So now what I actually did here is that how we can actually, from the angiogram, determine and classify which of the pixels belong to the tool pixels and which other ones belong to the background pixel. Originally, there has been a lot of intensity-based methods that are being used, like for example, in order to improve the contrast of the image, techniques like normalization, like global contrast normalization or noise suppression for artifact removal, and as well contrast enhancement are being used. And this is always done in the first stage. So in my approach, I propose a three-phase technique whereby we have to carry out sequential frame preprocessing. The essence of the preprocessing here is to ensure that the images or the angiograms actually are of good quality, and it's relatively easier for the model to be able to classify each of the pixels as either being for the tool. When I say tool, it will be guidewire or catheter, or it's actually part of the background, which is other pixels that does not belong to the tool class. Now, if that can be done successfully, I also move to using a vessel-ness measurement approach and analysis, which is used to determine the tubular structures in the angiogram, and then those tubular structures can be regarded as part of the tools, and the other ones that don't make a tubular structure can actually be regarded as part of the background. And lastly, I came up with using guidewire detection and tracking, perform guidewire detection and tracking, which is to actually allow the surgeon to be able to track the movement of the tool in the angiogram. Now, the first stage is preprocessing, which is typically common in most imaging process or image methods or image tasks. Now, the next stage, which is the main contribution in this study, was that how can we actually measure the vessel-ness, that is the tubular structure in the angiogram. So for that, I actually propose using an anisotropic filtering method, whereby we can actually filter each of the angiograms first to enhance the contrast of the intensity in the angiograms, and then this can allow us to be able to identify the geometric features of both the anatomical and as well as pathological structures in that angiograms. And if we know this, that means we can actually characterize and understand each of the other pixels in the angiogram. Now, to do that one, I actually started with if we have this kind of equation on this slide, which is a typical Taylor series, and we can expand that in the neighborhood of each of the pixels in an angiogram, we can use from the gradient vector of this Taylor series, we can use the gradient, its gradient vector to actually know which of those points belongs to the tool pixel or which other points belong to the background pixels. So what we did was to compute the Hessian matrix along both the diagonal axis and the principal diagonal axis of each of those points, and determining if a point can be classified as being part of the guide wire or other tool structures in the angiogram, or it belongs to part of the background. So with this, we actually carry out the second derivative of a Gaussian kernel, which is to measure the pixels contrast values of around that kernel probe at a given scale, and then we can use that to determine, based on the ASM value, if that pixel has a vessel-ness measure that can be made to determine as part of the tool, or otherwise it's part of the background. Now, once that is done, we also use a Frangi filter. Now, the Frangi filter here uses a multi-scale approach to determining if a point actually belongs to part of the tool or part of the background. And with that, we can actually be able to classify each of the pixels to being part of the tool and part of the background. Now, one problem with using this kind of intensity-based method is that there is a high level of disconnectivity among each of the pixels that belongs to a certain class. Let's say, for instance, the tool. And then if this tool pixels are actually disconnected, it's quite hard to be able to track its navigation in a single angiogram. Now, the first thing is we need to be able to determine each of the pixels that actually belongs to the tool and each of the pixels that belongs to the background. So for that, I propose a concept of using, I use the concept of using the minimal and maximal analysis, which is a typical extreme modeling, which is used for tool delineation. What this means is that all the tool pixels around the certain point where those pixel values are flat could actually be regarded as a background, and all the regions where the pixel value start to increase can be actually regarded as part of the tool or the foreground. So with that, we used valleys, which are areas where the point of those pixel value starts to increase as part of the tool pixels, and those other areas where the pixel points values start flat or reduces, or decreases as part of the ridge, that is the background. Now with this, we can actually understand the classification result as having either valley point or ridge point, that is either foreground pixel or a background pixel. Now, if we add that, how about the problem of disconnectivity, which is still a big problem? Now, to solve that problem, what I had to do was to first dilate each of the pixels that belongs to the valley. By dilating it, we can reduce the space, the pixel space between the disconnected fragment of the tool in the angiogram. And then those points that are still disconnected after dilation are typically regarded as other structures other anatomical structures in that angiogram, whereas the valley-like points that are connected after dilation can be regarded as a continuous part of the tool in the angiogram. And with this, we can actually calculate the position of each of the tool pixels, and as well as its orientation for each angiogram. Now with this, we carry out a study by using a robotic system built in the lab to carry out a catheterization procedure in rabbits. We had the procedure in 6 rabbits, and we carried out 12 different navigation procedures. And with that, we recorded all the angiograms, and I used this proposed model to segment the tool pixels away from the background pixels. One good thing is that now we have a single model. We have to tune a whole lot of parameters to ensure it works well for each of the sequences, and that gives high specificity, right? Of course, I was really happy when I had this result then. But then by also analyzing some of the other metrics that we have here, you can see that the model has some challenges. For example, sensitivity looks a bit good in these areas. For example, you can see sensitivity looks a bit good in these areas, right? But then when you consider all other sequences, the sensitivity value is quite low, which means this kind of approach cannot be generalized. We have a single sequence of angiograms. We have to tune all those parameters to make the model to be able to work effectively. And that can also be confirmed with the false discovery value, which of course looks moderately like average across the whole of the angiograms that we have. Now with that, I typically see that no matter how much I try to tune using this intensity-based approach, we cannot have a well-generalized model. And that was what moved me to using deep learning approaches. Now, before getting to that, I also had a lot of comparison studies that I did. For instance, I tried to compare the result or the outcome of the proposed method with some of the existing methods that had been used for the similar problems. And we found that this method actually has a better performance in terms of several metrics. And for instance, when we look at the area under curve, it has about more than 75% area under curve, which is quite greater than every of the other existing method that has been used for similar problem. Of course, most of these methods were used for retinal vessels, whereas in this project, we focus on cardiovascular vessels. Now, these are the output from each of those models. You can see that the segmentation result from the proposed method actually is better in terms of the discrimination of the tool pixels away from the background pixels. Most of the other pixels are very noisy. This can be due to the fact that they were actually proposed for retinal vessels. And of course, we actually ensure that we used all the parameters as they were presented in those papers when implementing the models. So one reason could be because they were implemented for retinal vessels. And of course, some are also implemented for cardiovascular, but cardiovascular vessels, not tools in the cardiovascular angiograms. Now, having observed that we cannot have a generalized model using such intensity-based analytics, I also proposed how can we use deep learning methods. And this is where I started with the concept of how we can develop a multilateral branch network. Now, what I had to do here is that I had a few graduate students working with me, including a master student who was a visiting student in our lab. Then I had them carry out a review on seeing some of the existing deep learning methods that are being used, especially in biomedical imaging research area. And then we surveyed networks like the fully convolutional neural network, SegNet, UNet++, UNet, CENet, and we found that one thing is that these networks can actually be used to, develop a more generalizable model that can solve segmentation problem for multiple angiograms that are obtained for from different procedures. Now, what I understood also is that the foreground that we have in this kind of data sets actually solve a class imbalance problem. Class imbalance problem is when the number of the when number of the one particular class in an angiogram, for instance, is much more than the other classes. For instance, the number of 2 pixels that we have is quite lower to that of the background pixel. So this is actually a class imbalance problem that needs to also be, catered for when developing such a model. So what we also did was to look into model that can actually address this kind of decreased size of feature map due to its pooling. So we task ourselves to see if performing multiple unpooling operation can be appropriately developed for a pixel level classification or segmentation task like this. So we explored using this model or architecture, which is called the DeepLab-V3. Now, it has some specific features such as the atriospatial pyramid pooling, which can also be done at multiple scales. So this can offer a form of contextual feature learning, whereby we can learn features or get feature maps around different kind of classes in a given angiogram. Now, this is the structure that we have in the DeepLab-V3, which was presented during the ECCV in 2018. And one specific feature about it is that it allows having multiple flows, in the encoder structure of the network, and each of these flows could actually have single lateral blocks of convolutional layers, and not just convolutional layers, even using separable convolutional layers in those lateral blocks. So we, based on this, see that it has very good performance in computer vision tasks. How can we also import such thing use it to to solve the problem we have in the medical image for our cardiovascular imaging task? Now, based on that, we also developed this multilateral branch segmentation network. And one of the main differences is that rather than having to use just a single lateral block for each of those, layer for each of those blocks, in our own case, we use multiple lateral blocks for each of those blocks that we have. Now, typically, we have added a parallel separable convolutions in all of those entry flow, middle flow, and as well as the exit flow. And then we try to integrate a batch normalization with the convolutional layers to stabilize the acceleration, the learning, and accelerate the learning progress in the model. And at the same time, we replace the depthwise separable convolution with a combination of pointwise convolution and as well as depth-wise convolution with batch norm regularization in our own model, which are the typical main differences in the encoder. Also, with the decoder, we use multiple upsampling with multi-scale approach. Now, we also use the atrios convolution network just as we have in the DeepLab-V. And what that means is that rather than using just the original convolution approach with a dilation rate of R as 1, we could actually have multiple O's in the output of our convolutions, which can enhance generating diverse features, and as well as we can have a rich feature map that can be used to perform the segmentation task. For example, if we set the value of R to be 2 or R to be 3, the convolution map becomes larger, and then we can have a diverse feature set as a result of our convolution operations. So aside that, we also looked at the decoder part and also make some new contribution. For example, we find a way that we can perform the multi-scale contextual extraction by using multiple bilinear upsampling processes, and each of these are actually performed on the feature maps to improve, the feature diversity in our feature that are gotten from the encoder and can be used to, improve the segmentation performance of our model. Aside that, we also added an attention mechanism, which was also introduced to solve the class imbalance problem, which is really specific to this kind of challenge, to this kind of task that we are trying to do. And also, we added a new loss function, which is an hybrid loss function that uses Dye's loss and as well as Stefanski loss with several regression parameters. Now, with this model, it's a very huge model, about 12 million parameters model at least. We were able to also set up another experiment whereby we carried out the catheterization procedures, now this time around in both rabbits and as well as in pig. And in addition to that, we also have some phantom experiment to see how we can, characterize the performance of the model. This is the experimental setup that we have. And then we could have the robotic system, which is this. This is the third generation of our robots back then. And then we could have it as a slave robot and a controller, which is, located at the cockpit with the surgeon outside of the catheterization lab. And then we have this robot placed in the same place with the patient. The patient here is the rabbit, and then we use that to navigate a typical guide wire and catheter within the vessels of, guide wire for the rabbit and both guide wire and catheter within the vessels of a pig. Now, with that, we train our model with all these model training parameters that we have trained on a GPU single computer, not an HPC, but then the memory of the GPU is quite huge. We have 2 cards, 48G each, which is quite sufficient to carry out all the research I've done at CAS. And then implemented this model using TensorFlow framework and Keras. And then we have this Adam optimizer with initial learning rates, which keeps reducing as we actually carry on with the training. So now with that, we can actually segment each of the, tool pixels from the angiogram. This is the original image here. This is the ground truth, which is also labeled by some of us and verified by some experts. And then we could actually have the model output as shown here. Now, one thing you would observe with the output of this deep learning approach is that the level of disconnectivity there is reduced far low compared to what we have when we use the intensity-based pixel analytics method. And that is number one. Number two is that you see the first 4 image input that we have A to D were gotten from the same experiment, and the angiograms we have in the experiment E and F were also gotten from different experiments. And yet, with a single model developed and trained with all these parameters, they can get a well-generalized and better performance compared with the intensity-based pixel analytics method, which is something that we felt is a very good contribution. And with that, we could actually carry out some further characterization of the model and its evaluation. For instance, in the experiment, we see that if we train that model on a single sequence, the same data set from a single sequence where we have partition for training and partition for validation, the performance of the model could reach as high as 90%, which is really good. And then if we have new sequences as our validation data set, and we have multiple sequences as a training data set, the validation reduced a little bit, but still very high at 84%, which shows that now this model can generalize well. And also, when we look further in some other metrics of running such a model on a single trial dataset and multiple trial datasets, we could see that the model that was trained on a single trial dataset and evaluated on a multiple trial datasets has lower performances, right? Unlike when we trained this same model on a single trial dataset and evaluated it on a single trial dataset and evaluated on a single trial dataset, the performances look good, right? Which is a 1-to-1 case. Now, by the time we have a 1-to-n case on a single trial dataset, the performance looks not good, right? So, which means that with this kind of approach, we cannot even ensure diversity of our training datasets if we don't have datasets from multiple trial datasets. Now, when we trained it on a multiple trial dataset and evaluated it on a multiple trial dataset, performance was very high, which shows that a model trained on this multiple trial dataset can have a better stability compared to when we have a model that is trained on a single trial dataset and still evaluated on multiple trial datasets. Another thing is that we brought in the concept of incremental learning, which is very close to curriculum learning in deep learning as a research field. Now, what we did there was that to have angiograms from multiple sequences in which data set from specific sequences were introduced into the model, used to train the model one at a time. Once we start with a set of sequence from a particular, set of data set from a particular sequence, and the model learns it right, we take that same model, fix some of the layers in the model, and then use another data set to retrain the model without allowing it to forget what it has learned in the previous training session. So with incremental learning training data set, we can actually achieve a high accuracy. But then the strategy here is that we allow the model to learn the easy cases first before moving to the hard cases. When we inverted it using case of, we have hard cases, for example, small number of data sets, and then later on, big number of data sets, the performance was not as good as this. Right? So now this is one thing that we also observed while developing the model. And again, we confirmed the generation of this model by using different kinds of data sets from different kinds of configuration. For example, we have an in vitro experiment whereby we use this phantom to carry out the catheterization procedure and navigated both guide wire and catheter in this phantom, recorded the images with a camera this time around, not an angiogram, not with X-ray imaging, with a camera this time around, and then we use those camera images to actually train our model and validate our model. Again, the performance is still as good as what we can see here. And in terms of pixel disconnectivity, it's quite very low, which shows the generalizability of the model. Similarly, we had a run in a pig and had multiple experiments done with that also, and then we still see that the model has a very good stability. So we compare this model's performance with many of the existing deep learning architectures that has been used to perform similar things, or at least in the field of computer vision. And we found that the model actually has a very good performance in terms of multiple metrics. For example, the MIOU was the highest, the precision recall area was quite high, and as well as the time it takes to process each of the angiograms was quite low. So, but then the number of parameters is still relatively high. For instance, if you compare the number of parameters that we have here as the UNet, which is the most used deep learning architecture in biomedical imaging, you'll see that the parameter is quite higher. We have about 12 million parameters. UNet has about 8 million parameters, which is quite high. One challenge with this is that we are unable to deploy this kind of architecture on edge devices such as a mobile phone, or when we are running our architecture on Raspberry Pi, which is on the robot itself. So this is one of the challenges, and we are trying to see how we can reduce the parameters of this model. I had a discussion with Michelle today, and we're discussing about how we can use, for example, distillation technique to reduce this kind of parameters, which is something that we also explored. Now, we also have so many other experiments carried out to see the contribution of each of the components in the architecture. For example, the loss function contribution, we tried different types of loss function, and we found that using the hybrid method, the one that is proposed here, has better performance, not much more better than we compare to with combo loss, which is very similar to the same, very similar to what we have also used in this research. Again, we also looked at some of the major components in the architecture itself. For example, when we look at the output stride, when we reduce from 16 to 8, 16 has the best performance. I'm not showing for 8, it's in the paper. When we look at, for example, some other components that we also used in the model, we see that the last configuration that we used, when we combine all those components, actually has a better performance. And this is why we actually adopted this configuration in the ablation study. Now, the problem with that method is that we need surgeons, we need experts to annotate our ground truth data, and they are not available. They are never available for this kind of thing. So we're looking into a way whereby we can actually have data sets that are not, still being able to use a data set that is not completely labeled, for example, to still train such a model and get something that can be used to solve such problem. Now we shifted ground a little bit from rather having multiple lateral branches in our encoder now to having the lateral branches in our decoder, right? And how did we do that? We look into weakly-supervised learning. In weakly-supervised learning, you can have an incomplete annotations and use that to train a machine learning or deep learning model and still have a performance that is as close as possible to when you use fully supervised or full signals to train such a model. In literature, we found that there has been a lot of works also done in this area, and we found that, for instance, what Low et al. Did in 2021 was very close to what we are trying to do here, but rather they have used a dual decoder branch, and then we see like, how can we step up to multiple decoders, starting from 3 decoders. Now, for that, we propose this architecture whereby we can have a single encoder this time around feeding multiple decoders, right? We can have at least 3 decoders in this kind of architecture, rather than 2 decoders that Low et al. Had in their own study. Now, what we are trying to do here is that we can take one of these decoder, for example, this first decoder, as the main decoder, whereas all other decoders can be taken as auxiliary decoder. And then each one of them will give their results, and we can combine all those results as a sample to find an average as the output of the model, which is the main methodology that we actually proposed there. This study was also presented earlier this year. Now, we can use different kinds of backbones. All of those backbones that are presented earlier on can be used for this technique, but we are focused on using a modified UNet architecture because the master student that I co-trained at CAS actually developed this model by modifying the original unit, expanded the layers a little bit, and then we have a modified approach that serves well in the area of cardiovascular image analytics also. Now, so we took that as our backbone and used it in this study. So what we have to do is that we want to generate pseudo labels. Pseudo labels is a situation whereby we can generate supervision signals that are not fully annotated, unlike when we have full signals, right? So from those pseudo labels, we can actually use that weak signals to generate pseudo labels by the other decoders and use those pseudo labels to train the other decoders. So to do that, we first strategize how we can learn from the annotated pixels. Again, not fully labeled annotation, not fully annotated images, right? So how can we learn from those pixels that are annotated in those ground truth datasets? And from that, if we're able to learn from that, from this cross entropy operation, we can use that to supervise the, we can use that to supervise the other auxiliary decoders, and then use the result from all those three decoders, combine them to, get the output of our model. Now, once we're able to get the pseudo labels, the next is how can we pairwise the pseudo labels supervision, use the result from the main decoder to train the other auxiliary decoders, and then combine all the output from all those three decoders. With this, we actually have those three decoders have some differences. For example, we introduce several dropout layers to all of the auxiliary decoders in different versions, which is the main difference between the auxiliary decoder and the main decoder. And as a result of that, the output of the decoders are being perturbed. So it can bring in a lot of noises and differences in their output. So we need to also introduce the concept of shared consistency, which is an approach to find a kind of average or to normalize to reduce the differences between all of those three decoders, which is what we did with this equation shown on this slide. And from that, we also tested our proposed model. Again, we had the experiment that we have used for the second paper that I presented to, the data set that were obtained from it. We used those data sets to validate the weakly supervised learning. And in addition to that, we also got another data set, which is this time around, another phantom data set, which is a public data set that is available on the internet. We used that data set also to validate model. And from results, this is a view of the annotation that we use this time around. Rather than having a fully annotated ground truth data set, we have partial labelings as our weakly supervised training signals. And then we use the parameters that are here to train the model, and we have very good results. For example, when we train the model for a rabbit dataset, we have about 70% MIOU, which is very close to what we have under a fully supervised network, which is actually 78.78%. Similarly, when we use the same dataset for a pig the dataset that are obtained in the pig experiment, we also have something that's very close to the fully supervised network. And as well as for the public dataset, which is the phantom dataset, also gives a very good performance. Of course, the performance of the model on that phantom dataset is quite large because there is high dilation. That the number of 2 pixels is quite high in those angiograms. By default, angiogram is 250 by 250 pixels, and number of foreground pixels is quite high compared to the rabbit dataset that is 1560 by 1440 pixels, and number of foreground pixels is very small. Now, with that also, we also evaluated and compared the results with some of the existing methods existing weakly supervised method. And we found that the proposed method also has, like I've said, a very close performance with the fully supervised method. As you can see here, for example, the MIOU, and in terms of visualization, the output was quite better. This is for the case of the fully supervised output, and this is the case of a model that was trained under the weakly supervised method. And we compare with some of the other existing methods, which are also trained with the weakly supervised approach, and then see that our proposed model has a better performance. For instance, we characterize it with the mean margin. The mean margin here is the difference, the average difference between the fully supervised network and as well as weakly supervised networks, and so that the mean margin for our proposed model is quite low. In terms of the mean percentage difference, also, for instance, we've gotten about 16% for the rabbit data set, and as well as we have gotten about 27% and 60% for the other two methods, which is quite very high. Now, we also had ablation studies to see how the different components in the model add contributions into the model's performance. For instance, we check the consistency value, which is the value that's used to control the consistency amongst the 3 decoders. We use different values and found that at 0.5, the performance is quite higher than every other consistency value that we had. Also, we check the performance of the model when we use a single decoder, multiple and 2 decoders, and as well as 3 decoders, and found that the performance of that 3 decoders has the best MIOU. So we also try to see about if we remove the consistency learning, the shared consistency learning from the network. For instance, when we try every other component and just remove the shared consistency learning, you can see that performance actually dropped significantly compared to what we have under when we have used shared consistency learning in the whole of the method, which is something that shows that the shared consistency approach also contributes to the performance of our model. Now, with this, we can actually deploy this kind of model, either the MLB, the original one, or the one that is trained under weakly-supervised method for navigation analytics in a robotic setup. We had a trial, which is part of the last paper that I just presented. This is a setup that we have. This is a setup for an in vitro study, a phantom-based study. We have our robotic system here. The master device is what we have here, and which is one that is located outside of the operational room. We have the slave device also, which is one that's located close to the patient. And in this case, our patient is actually the phantom that we have in this box. Now, for the case of imaging, we have used a camera in this setup, and the camera images are just passed directly into the model and use our deep learning model to perform the segmentation task in close to real time, in online. So as we carry out the catheterization procedure, you can see the model is able to segment the 2 pixels in the video directly without having to do it offline, as what we have done in the case of the MLB network, which shows that this kind of model can actually be used for visual analytics in the catheterization operation. Now we have done that for guidewire. We see that it has a very good result in online in an online catheterization process. Also, we tried that for a catheter. It also has a very good performance in terms of MIOU. Both are actually very good. Now, catheter always has better performance because of the number of 2 pixels in it are more than that of the guidewire, and this connectivity in catheter is actually quite high. So in terms of the processing time also, it's very similar because the model has a more stable performance for both tools, and then the connectivity is quite better for catheter. Like again, the number of 4 pixels is higher than the number of background pixels in catheter than when compared with guidewire. Also, we use some of the other existing backbones in this architecture rather than using the GSR unit only. We have tried the MLB net, which has multilateral encoder, and combining multilateral encoder now with multilateral decoder. Now, this gives a better performance to when we only have multilateral decoder or with weakly supervised learning. For instance, with a 25% annotation in an angiogram, our proposed method has about 62% MIOU, but then when we use the MLB network, which has multiple lateral encoder blocks, it also has a better performance under 25% annotation. Now, when we move to 50%, which is what we actually use in this study, you can see that the performance has also increased. Of course, the more we annotate in each of these angiograms, the better the model can learn. But what we aim at is how we can reduce the level of annotation that is needed before we can train a machine learning network. And then when we compare with some of the existing backbones also, we still found that the proposed backbone actually still maintain its better performance as presented in my students' paper back in 2021. So in conclusion, in this research track, what we have done basically is to see how we can improve a real-time visualization with visual analytics in the area of cardiovascular interventions. We have proposed several machine learning or deep learning networks, which has been tested and also has tried in a real-time study, and found that this can actually help in a catheterization lab. But then there are still a lot of work that needs to be done. Like, for example, this is the whole of the research pathway to what we have now, what I've presented today. For instance, we started with using intensity-based method and then graduated to using MLB with multilateral encoder, and then again we try with multilateral decoder. Now, if we have this at Chinese Academy of Sciences, where we actually have the robotic setup, this kind of research seems not with what I can move forward here at CQ, because we don't have the robotic setup. And because of that, I want to look into another aspect of cardiovascular intervention, which is how can we carry out disease diagnosis, disease detection, characterization in typical images that we have from the same or similar procedures, right? For instance, diseases like plaque, like stenosis, are also some of the coronary artery-related diseases that are also killing humans today. So my concept is how can we actually look into building a generalizable machine learning model that can be used to perform multiple tasks, such as, for instance, we can have the CTA or MRA, and then we can perform tasks such as segmentation of vessels this time around, and then we can characterize each of the vessels to see if a patient is suffering from stenosis or plaque, and then we can characterize such a plaque within the CTA image. Now, to do this, originally what is found in literature is that we have developed several machine learning models, right? Now, my concept is how about if you can have a meta-learning concept which is in machine learning. Meta learning means developing a model that learns how to learn. So the machine learning model itself can actually learn how to perform certain tasks from a given threshold. For instance, we pre-train a model to this level, and then from this level, we can adapt it to go in different directions, right? So we don't have to necessarily train a model from scratch every time we want to focus on a specific task. And this is what I'm aiming at looking in the next few years. And also, we can also bring in the concept of semi-supervised modeling, especially, for example, for a multi-tool segmentation, which I'm currently working on, and the result is also getting better, but still working on the research right now. This is where I would end my presentation for today. Thank you very much for listening, and I'm much more than happy to answer your questions.
Thank you very much, Rolat, for the great presentation. It shows the work you're doing, the great work you're doing. So now I would like the audience to ask questions.